Yes. So this is our textbook, and it's certainly one of the very useful references you could have in your whole journey of learning, whether it's an undergraduate, graduate, or research level. It has a wealth of information. It's a very well written book. Strongly recommended. But it's not the only book there. For example, this is another book. This is a very well-known book. It used to be the standard textbook for teaching the material at Stanford University. Those are three very well-known guys. Graham passed away recently, a few years ago. Caruth is a pretty old guy. He's one of the fathers of computer science, and one of those perfectionists in the authoring and writing. Patashnik is also a very well-known guy. So this book is very interesting. I won't claim that it covers all the topics covered in our textbook, but it has solutions to all the exercises, except those which don't have a solution at all, like they are open problems. And it keeps those interesting notes, side notes like this and that, which were originally written by students who had to review this script back then, because I think the early versions of this book were written in the 70s. Many things can be said about this book. There is also the interesting Discrete Mathematics book by Susan Epp. She is very good at simplifying things and stating concepts in a very simplistic way. If you'd like, I mean, if you had difficulty understanding concepts, it's also a nice reference for you. Now let me ask you, please, can you see the slides?
Yes.
Good. Good. So those slides were prepared by the author of our book. We will be going hand in hand with the table of contents of our book, sometimes skipping some sections just to save time, giving priority to other material which may be more related to your fields of study. So how to do well in this course? For you to do well, you need to attend the lecture, make sure that you understand what's being discussed. But most importantly, to do your homework of solving exercises. If you don't practice, then you would lose the skill. And obviously, the skill of solving problems, thinking of problems and solving them, is the skill which we want to take out in the exam. It is that thing which will be examined in the exam. So I would recommend that you have the book on your shelf and be prepared always to solve problems. Check that you did well by consulting the back of the book here. See that you solved the problem correctly, see the number and see did you solve it correctly or not. And then solve more problems as you go on. You don't need to solve the 40 plus maybe problems, and you don't need to go in the hardest problems. Problems here are classified into a spectrum in their difficulty. As you go on, they get harder. Some of them are pretty hard, some of them are extremely hard. So yeah, I mean, it could be good if you do one of the extremely hard ones at least once in the semester. That would be good. So make sure to solve problems. The more problems you solve, the more skill you acquire, and the deeper your understanding would be, and the better you are familiarized with the course contents. So what is discrete mathematics? Yeah, we call it discrete structures here, but yeah, it's pretty harmless to switch between names. It is that part of mathematics devoted to studying discrete concepts and discrete notions, discrete objects. Yeah, as I mentioned, integers are discrete as opposed to real numbers. What if we are interested in counting the possible solutions of a certain problem? What if we are interested in counting how many steps a certain algorithm takes before it finds the solution? Imagine that you want to travel from Jordan to Germany. I mean, without using an aeroplane, without using any flight, you want to travel by car. You may travel to the north, reaching Syria, then further to the north, reaching Turkey, then further to the north, reaching Greece or Bulgaria, then further to the north, and to the west, until you reach Germany. So this is one possible path. And another path, perhaps, if you go to the west, reaching Palestine, to go to the west, maybe you will bump to the sea. And I mean, if you keep going to the west, then going to the north, further to the north, yeah. What if you switch, for example, to a southern part, then switching back to the northern part because, for example, it's cheaper. So there are multiple paths you can follow to travel from Jordan to Germany. How many paths are there? And which path offers the lowest cost? Yeah. Counting those things and finding solutions to such questions belongs to discrete mathematics. So discrete mathematics is a very, very wide umbrella, as we will see shortly. If you have an algorithm, like a computer program, which sorts a list, so it is given an unsorted list, and then this list is sorted by this program. How many steps does it take to sort the list? 10 steps, 12 steps, 20, 100? What if the list has n elements? How many steps with respect to n? And why? Imagine that I came to this lecture room and we wanted to pick 2 male students and 2 female students, for example, to represent the university in a conference. In how many ways can we choose such students randomly? So such mathematical concepts belong to computer science and engineering. I would like to emphasize the fact that whenever I'm saying computer science, then computer engineering is typically meant. Computer engineering, then computer science is typically meant. There is no obvious barrier which separates those fields from each other. Artificial intelligence, software engineering, cybersecurity, computer science and engineering, computer science and software systems, computer information systems, and yeah, these countless names, they boil down to very common things among them. So I would say that the mathematical background, as mentioned here, is quite relevant and useful. It formulates your mindset, your computer scientific mindset, and it is highly relevant to what you will be learning in your studies further in your upcoming semesters. These are typical questions which are addressed in a discrete mathematical setting. So in how many ways you can choose a password, giving certain restrictions. And how many internet addresses are there? I would ask you now, which standard offers more addresses? The IPv4 or the IPv6? No answer. Of course, the IPv6. We may be also interested in calculating the probability. The probability is quite interesting. The statistical probability studies are quite interesting when we want to know, when we want to answer the following question. Given an algorithm, on average, how many steps does it take to solve the problem? So how many steps does it take is one question. On average, how many steps does it take is another question. Is there a link between two computers in a network? There might be a small network here, connected to another small network there, connected to another small network there, and so on and so forth. Many interconnected networks. But as you examine the points of connection, given a computer, call it A, located here, and another computer, call it B, located far there, is there a link which can be traced between A and B? It is not that discrete mathematics is concerned with computer networks, but discrete mathematics can model this problem abstractly without talking about computers. We can talk about what's called graphs, and we can represent those connections as edges. So graphs are nodes and edges. Nodes like circles connected via edges. And those edges tell you, is there a connection or not? How can I detect a spam in a message? You can detect a pattern of those spam messages, and you can start identifying them. How can you encrypt a message? Oh, that's a big thing. There is a whole field of study called cryptography and cryptology, which studies how you can make a text unreadable, so that if you get a grip of that text, you cannot read it unless you are the legitimate recipient of that message. How can you build a circuit? Well, a digital circuit here. A circuit which has components, what's called AND or XOR NOT gates. It has logic gates as components, and it does the task of adding two integers, subtracting two integers, multiplying, or doing other things. Actually, this, in a way or another, belongs to discrete mathematics, but it is also under the umbrella of the topic of digital logic design. It is a standalone course, which you will be studying perhaps in this semester or next semester. So we won't be spending much time talking about it. Encryption and decryption is also a standalone course taught to fourth year cybersecurity track students. It was taught last semester, actually. So if we talk about it, we will be talking about it briefly. Other things like the shortest path or the path with the lowest cost between 2 points. And the path is not just a connection. A path is a connection which involves multiple stops. Is it better to go 1, 2, 3 or to go 1, 4, 7, 2, 3? And so on. or the shortest tour, which is like a cycle. It's like moving 1, 2, 3, 4, 5, 6, 7, 8, 1 again. Okay. Also, we may get to know about representing English alphabets as meaningful stuff, not meaningful to us as human beings, but meaningful to computers so that computers can reason about them. For example, if you say, Jordan is a country in the Arab world, this is meaningful to human beings. But to computers, what is it? It's just a string of ASCII characters. This is pretty meaningless unless you start teaching computers that this is not just a string. Those are words, and those are connectives. And this is a noun, and this is a verb, this is an adverb, this is an adjective, this is, and so on. So you start classifying things to computers. Then computers can start doing their homework of thinking or reasoning or analyzing about different statements. So it can do the task of reasoning on your behalf. And that's why, of course, this links to artificial intelligence. And that's like the foundational roots of how large language models are built. Because there is a huge work behind them. But before you can start with the basics, you cannot proceed. Large language models like what? Anyone would like to answer?
ChatGPT.
Good. Can you give me another example?
Gemini.
Excellent. Gemini is made by Google. And have you got to know about that Chinese competitor? What is it called?
DeepSeek, doctor?
Exactly. Exactly. So DeepSeek caused a lot of embarrassment to the competitors. Other things which can be also interesting is to count the number of steps required for an algorithm to finish. And sometimes the number of steps is infinity. So some algorithms find no end. And this tells you that this algorithm needs to be avoided. Also, as we learn discrete mathematics, we learn proof techniques. So we learn that given a certain statement, can you prove that it is true? It might be something which you've been using for a while, but can you prove it? And given a certain proof, is it actually a correct proof or a bogus proof, which is just a pointless compilation of statements which do not link to each other? Here, for example, can you prove that we've got infinitely many prime numbers? So prime numbers are not finite. Can you prove that? Yeah. And more interestingly, can you prove that a certain algorithm works correctly? I'll give you an example. Imagine that you asked your friend who took the class CS116 with you. You asked him to write a program which receives two numbers, multiplies them, and gives you back the result. So you tested the program of your friend. It asked you to input two numbers. You entered 5 and 2. This should produce 10. And yeah, it did produce 10. It produced 10 on the screen. So you took it for granted. You trusted your friend, and you were sure that this program always works well. And no, your friend was tampering with you. Although the program receives two numbers, it doesn't multiply whatsoever. It just receives any two numbers and then it prints 10. If you input 5 and 5, that should be 25. It gives you back 10. 5 and 0, that gives you back 10. 1 and 100 gives you back 10. So apparently, this program doesn't do anything. It doesn't do anything correctly. It just produces the same result. And it gives you the false impression that it multiplies two numbers. You took the program and you modified it into your own version, and you ended up producing a correct program. Now you know that the program written by your friend can only give you the false impression that it works correctly when you enter, for example, 5 and 2 or 10 and 1. So it gives you back 10. But the program is not correct. Your version of the program is correct because it works for all cases. This was a simplistic didactic example. You may consider a program which sorts a list. It sorts a list of numbers, and it works for most lists. But maybe if you give it a list of floating numbers, it would fail a little bit. If you give it a list of numbers, maybe complex numbers, it would fail miserably. So there is something with the correctness of that program. Can we capture the whole notion of algorithm mathematically and generate a proof, a rigorous, airtight mathematical proof that this program actually always produces the correct result? So this is a whole field of study, actually. It's called program correctness or algorithmic correctness and program verification. Sometimes the programs are simple, sometimes they are quite complicated and sophisticated, composed of multiple parts. So verifying them is a very challenging task. But sometimes verifying them is essential for them to be used. What if the program is used in a critical system, like the system controlling the blood sugar levels of a patient, or controlling the heartbeats of a patient, controlling a nuclear reactor? Then there is no room for making mistakes. What things you would learn as you learn discrete mathematics? You would learn mathematical reasoning. If you were given a sequence of statements which together constitute a proof, then you will be able to recognize whether this proof is actually a proof or just not a proof. I can give you a bogus proof that 1 equals 0. You can find many such things on the internet. Other things you would learn is the combinatorial analysis, and sometimes called combinatorics. So consider the following example. Given 4 people and a round table, which can take 4 people, in how many ways you can arrange them on that table so that this person doesn't sit opposite to that person? given a box which consists of 10 balls, billiard balls. 5 of them are green, and 2 of them are red, and 3 of them are white. In how many ways you can select 4 of these balls so that at least 2 of them are green? So this part of mathematics is called counting, the art of counting, or counting techniques, officially called combinatorics. Given a list of numbers, in how many ways you can rearrange the elements of that list so that this element remains in the middle. And as you learn discrete math, you learn what's called discrete structures, after which this course was named. So discrete structures is what? Are those mathematical objects which are of a discrete nature, like sets, permutations. A permutation is just a rearrangement, relations, given a set and another set. Is there a map between the first set and the second set? Can you map them? Yeah, there could be a map. For example, this is a list of numbers. And there is a list of the squares of numbers. This is 1, 2, 3, 4, 5. And this is 1, 2. This is 1, 4, 9, 16, 25, and so on. This is the list of integers, or natural numbers. This is the list of squares of integers. They can be mapped to them, and so on and so forth. Graphs. So graphs is not about graphics. Graphs is about things which look like this. Show you. So it's nodes and edges, like circles and lines connecting those circles. Trees are special cases of graphs when those edges have a direction and it's always pointing downwards. Finite state machines is a topic which is entirely studied in a separate course. We may visit in the last few lectures or may not visit at all, but it's just the foundations of computing and how computers work in a very abstract sense. You would also learn in discrete mathematics that algorithmic thinking. This is touched gently in this course, but more substantially in the course of algorithms, which is maybe next year you will be taking, typically with Dr. Samer Nofel. You will learn how to solve problems by specifying a sequence of steps, which is by composing an algorithm. And you will get to learn why a certain algorithm is a better choice, why a certain algorithm takes more steps than the other algorithm. And you may be also exposed to the study of verifying whether an algorithm is actually a valid one or not, which is the notion of correctness. Well, as you study mathematics generally, you will get to learn that There are two types of mathematical studies. If you want to study mathematics for an undergraduate or a graduate degree, there are two types. There are two main paths you can go through. You can either study mathematics in a pure sense, mathematics for the purpose of mathematics. For example, studying new techniques for solving equations, new techniques for solving differential equations, considering advanced algebraic structures and how they are useful in a way or another. Topological structures and their connections to certain algebraic structures. But you may also study applications of mathematics, which are countless. This is called applied math. Before you can apply mathematics to a certain problem, that problem needs to be modeled. That is, that problem needs to be represented as a mathematical object. Then you can apply the mathematical tools on that problem. So modeling and applying mathematical tools is just a very vast field. This may include biology, chemistry, linguistics, and so on. To us, it's about computer science mainly. So once you learn discrete mathematics, you are given the foundations to study computer architecture. How? Whether you study logic, design, gates, whether you study them within the scope of this course, or you study them within the scope of the digital logic design course, I think it's typically taught by Dr. Ammar Gharaibeh. Then you get prepared to study the course of computer architecture and organization, which tells you how computers are built, how computers are constructed from electronic components. It also prepares you to the theoretical foundations of data structures. So data structures is a course that is taught using the language C++. That tells you how you can structure data within memory. Data can be structured as a stack, as a queue, as a list, as a linked list, as a linked stack, as a tree, as a binary tree. And how can you visit the data within a tree, traversal? These are all mathematical concepts. It prepares you for the course on algorithms. It prepares you for a course on programming language, that is programming language design, how to make a programming language, because to make a programming language or to build a compiler, as mentioned in the further point, you need to know how strings are handled and how state machines are constructed. Computer security is a vast field, and the subtopic of that field is cryptography. It's entirely based on mathematics, especially algebra and number theory. Databases, although they are recognized as applications, I mean, the area of database management is viewed by many people as something that is software level, application level, but databases is a topic that was developed by the notion of relational database. So relational databases are just relations, mathematical relations. This was developed, I think, back in the 70s at the IBM labs. Artificial intelligence, yes, of course, it is based on theoretical foundations, whether it was about reasoning and modeling things, or it was about machine learning and statistical inference, which is based on probability. Networking, whether it was about representing things as graphs, or whether it was about paths and routes. Graphics. Graphics is about a lot of mathematics. It's a lot of linear algebra. Linear algebra is visited gently, matrices and linear algebra within the scope of discrete mathematics. Game design. Game design is about, also it involves a lot of mathematics, and it's now becoming a whole field of study. There is a whole bachelor's degree in game design. Theory of computation. Theory of computation is a whole subject of study. It's heavily mathematical, and it tells you how computers operate, not from an electronic viewpoint, but from an abstract mathematical viewpoint at the very, very low level of computation, at the bare bone level. Interestingly, this course of discrete math, there is a twin course to it, which is not taught to computer science students. It is taught to mathematics major students. So that course could be named Foundations of Mathematics. They might be using the very same textbook, by the way. If you look in this textbook, it tells you how to use it for math students, how to use it for CS students. So we will just be reading those topics here within mathematics. Logic is just mathematical logic, truth or false, the truth of whether a certain argument is true or false. And set theory, yeah, we will be visiting this. Probability, we know it. Number theory, the study of integers, a very interesting topic. Abstract algebra, yeah, it's one of the central topics of math. Combinatorics, the art of counting. Graph theory, the study of graphs. Graphs is not graphics. Game theory it has nothing to do with game design. Game theory is about it's like an economic field of study. It was established by mathematicians, actually by the known mathematician John Nash. There was a movie about him. So two people who are interested to achieve benefit from something, and the benefit of one of them is against the benefit of the other. So each of them wants to maximize their benefit. And network optimization, it's a graph theory based applied math topic. The list can go on. So we can stop at this point, hoping that our next lecture, which would also be electronic, before next week, inshallah, we will be back to our lecture rooms. And we can stop the recording at this point.